Okay, well, let's get back to this. Sorry about the interruption, but it was getting long anyway, so you probably needed a break. So hopefully you've gone off, got a a cup of coffee or drink or whatever it is you want to do, and restarted the video. So yeah, let's get started here and pick up where we left off. So here's the table of thermodynamic properties that we went through. I've backed up a few slides here, so we've found that 2 and 3 are at the same pressure, 3 and 4 are the same enthalpy, and 1 and 2 are the same entropy. And as we've pointed out, 2 is a difficult one to get to. Okay, so let's take a couple minutes to talk about that. So we go into what's called the superheat tables, the part outside the saturation region. So here are the superheat tables for 410A, and you can see we've got it at 400 degrees Fahrenheit and 450 degrees Fahrenheit. I'm sorry, 400 psia, 450 psia. We're at 431, so we're going to be somewhere in between those two. And we go down the entropy columns. Remember, we're looking for an entropy of 2, 4, 5, 9. And we say, well, we're between these two, between 130 and 140 on the 400 psi. But we're over here between 150 and 160 on this one. So this double interpolation means we have to go and find where this entropy fits here, come up with that temperature. So somewhere, it's just eyeballing this here, it's pretty close to 140, right? So it's going to be, the 139-ish temperature. Over here, we'll have to find the pressure, the temperature that entropy applies to, so probably closer to 150, so 151-ish, okay? And then find the enthalpies as well, and then use the other interpolation to get between the two pressures, between 400 and 450, and look that up. If you didn't follow the details of that, it's because it's a lot easier to actually do than just articulate. So I encourage you to just go ahead and from these tables, and you can find them on the PDF, go ahead and do that interpolation. And what you end up with, I'll leave this as an exercise for you, is that the temperature is 147 degrees Fahrenheit, and the enthalpy is 133.6. Also find that the quality of state 4 is 0.33. So it's kind of, again, this graph isn't very good. It's probably over here somewhere. Okay, so we want to complete the thermodynamic exercise. Other things. So I'm going to leave this for you. I'm going to wrap this up. I'll follow up with a little email to you to talk about as well. But complete the thermodynamic analysis from that table that we put together here. First of all, verify that. Make sure you know how to do that, because we're going to be doing more of this as we go along. Find the compressor work. Find the COP. You can actually, and keep in mind that these are all per pound, okay? This is all it's called a specific analysis. So you get the specific heat transfer, the specific work. We get the heat transfer per pound of refrigerant. We get the work the compressor work per pound of refrigerant. But we also know what Q is, right? We know it's 10,150 BTUs per hour, so we can back out what the mass flow rate through the system is, and finish that. So we can find a COP that our thermodynamic analysis suggests it should be. And so I want to look at what it is relative to the specs of the unit, and then postulate on why they're different. And I assure you they're going to be different. And let's talk about that, and we'll make that part of our discussion as we go along. One last thing here. As much as I love double interpolation and all the cranking through the calculators, I just ran across this week, and let's face it, this is so cool. So the Wisconsin Industrial Refrigeration Center has this little thing of properties. You can just put in any two thermodynamic properties, and it gives you all the rest of them. So it makes the superheat super easy. So what the heck? Let's go with the modern age and use that if you want to. And so let's. I think I've only got one or two slides left. So let's take a quick look here of how you control these things. These things aren't just open loop. Turns out you can make these valves variable, which controls the rate at which the refrigeration is moving through here, and you do it in a way to make sure that what's coming out of the evaporator is superheated, so you don't get liquid in here. So nearly all refrigerators, home air conditioning units, commercial freezer cases and refrigerator cases in grocery stores have this thing. It's called a thermal expansion valve, which is controlled by a bulb here. It's not electrical. It's all it actually has refrigerant in this line. It's a separate refrigerant system that lets the water or the heat from the superheat boils the refrigerant, exerts a pressure, and it changes the valve opening. And it's a feedback control system, and it's not on off. It's variable. It varies the size of this orifice to meter just the right amount of refrigerant through to get just the right amount of superheat here. If you get too much refrigerant, you get liquid come down here. You get not enough, it gets too hot. And so you want to make sure you do things just right. And there's other things you'll see. There's things called receivers that help separate the liquid and the vapor. There's sight glasses, so you can actually watch the stuff go through. Oil separators. But we've talked a little bit about what the hardware looks like before, and we'll just cover this as appropriate as we go along. Yeah, so we'll talk about the interaction between the compressor, the evaporator, and the condenser, and how that works out. In fact, there's an interesting interaction from an efficiency standpoint between the operation of a condenser and the operation of a compressor. So you can put more energy into a condenser and drive it closer to the wet bulb, which lowers the pressure at the condenser, which makes the compressor work less. And so there's a trade-off between condenser work and compressor work, and there's usually a sweet spot. There's a place where the two of them are operating the best you can. And so we'll talk about that as well. So that's it. Sorry I had to break this up into two videos, but I think that'll work out just fine. Again, by the time you see this, I will have posted a little more description of what I want you to do for that homework assignment. It's pretty straightforward. And that's it. Thanks.